Welcome to the another session of thermodynamics class. Here we are continuing the previous classes problems itself. Taking up a new problem. Let us understand the problem by reading it once. 1 kg of air contained in a closed system at 100 kilopascal and 300 Kelvin. So the mass of air which is contained in the cylinder is of 1 kg, and at the present it is at a pressure of 100 kilopascal and its temperature is of 300 degree Kelvin. Is compressed isothermally till the volume halves. So let me represent this in a pictorial format. There is a piston cylinder arrangement. So now in this problem the system is undergoing compression. So it is very easy to understand or to estimate. The piston initially is at higher volume and finally it comes down to minimal volume, or the volume will get reduced. So here I will mark it as state 1 position of the piston. So after compressing the gas isothermally till the volume halves. So now the initial volume is the available volume at this particular point. Now the final volume should be half of the initial volume. That means to say I need to place the piston in such a way that the volume available to the left of the piston should be exactly half of the initial volume. Now I will say this is the second position of the piston. Now let me say this is volume V2 and let me say this as volume V1. Now we can, by pictorial comparison itself, we can say that the volume V2 is half of the volume V1, and that is what is the problem saying about. And the volume has been reduced by isothermal compression. Okay. During this process, it is also stirred with a torque of 1 Newton meter at an RPM of 400. So how is the arrangement done? There is a stirrer which is provided for the stirring of the gas or which is for the stirring of the system. So compression means work done on the system. Even stirring of the gas also means work done on the system. So in the very first glimpse of reading the problem itself, we can understand both the works are negative work or both the work has been done on the system. Next, so this is running at a speed of n is equal to 400 RPM and the torque provided is 1 Newton meter. And the duration of time in which it is made to run is 1 hour. Continuously this is running for 1 complete hour. Okay. Calculate the net work done on the system. So what are the net work means? It is the summation of different processes or the different works which has been done by the system or done on the system. All cumulatively we call it as net work. Now in this problem we are witnessing two things which is done on the system, two types of work done on the system. One is isothermal compression. The next work is the stirring work which is done on the system. So we have listed the data, the mass which is the gas itself or the system mass, it is given of 1 kg. the pressure initial is 100 kilopascal, the temperature initially is 300 Kelvin, the volume, the final volume is half of the initial volume which has been represented mathematically. Then torque, I will express the torque as T suffix Q, so that I can easily differentiate the denotions between the temperature and torque. So then the speed which is represented by N is 400 rpm, time I am representing it by small t, okay, it is 1 hour. It can be also expressed in terms of second as 60 into 60, that is 60 minutes will be there in 1 hour, and in 1 minute there will be 60 seconds. So the total quantity of seconds in a time period of 1 hour will be 3600 seconds. So all the data has been written down. Now we are supposed to write a PV diagram which should be representing the displacement work. So anyhow we cannot write the PV diagram for stirring work, we can only draw the PV diagram for displacement work. Displacement in the sense, only when the volume is going to change, only then there is a possibility of, or there can be a displacement. Without change in volume there is no concept of displacement. So here 1 hour I will just represent it as 3600 seconds. Now for the PV diagram, to represent the isothermal compression. Now the initial volume is at this point, here this point I will represent it as 1, and the final volume is at this point, and the initial pressure is, we know that it is 100 kilopascal. Once the compression takes place, it is a very clear guess the pressure also rises. Why? Because the volume is reducing. So the pressure will be much more higher, and the curvature of the isothermal process looks in this fashion. So the arrowhead is pointing towards left, and the area under the work, the area under the curve, that is the hatched portion, is representing, I can say it as W displacement. The area which is equivalent under the curve 1 to 2, now I will call this as displacement work. So let us, after writing all these things, let us start with the problem. We know that W net is equal to, for this problem there are only 2 work transactions happening, and both the works are working on the system. So one is the compression work and the another is stirring work. So first let us find the value of W displacement, and then later on we can find the value of W stir or stirring work. So here the work displacement, we have taken this formula. The reason is the compression is happening isothermally. That is the reason why we have taken this equation. So isothermal work transfer equation is P1 V1 ln of final volume by initial volume, that is V2 by V1. So here the pressure I am implementing it in kilopascal. So finally I should be aware that the work unit also comes out in kilojoules. Suppose if I just apply this in terms of Pascal, I will just get it in terms of joules. So that unit consistency should be there available in each and every step of the problem. Even a small unit consistency mistake, if it happens anywhere in between the problem, there is all the chance for the end result to go wrong. So saying that, substituting all the values, so here before substituting into this equation, here V1 and V2 relation has been given, but individual values has not been mentioned. The relation between V1 and V2 is, that is, the final volume is half that of initial volume. Only that relation we know, but we don't know the individual value of V1 and V2. So finding any one, that is V1 or V2, I can find the another volume. So we have now left with, now V1 and V2 both are unknown. We need to find any one. For that intention, what we have done, we know the temperature at the initial stage, volume at the initial stage, temperature is known, pressure is known, mass is known, R is known. The only unknown thing is V1. So taking this equation's help, I am trying to find the value of V1 by applying ideal gas equation. Now, since I have placed here as M, the volume what I am going to get is total volume, and the unit comes out to be in meter cube. And the R value is given in terms of kilojoule per kg Kelvin. So it is to be taken care that the pressure also should be substituted in terms of kilopascal to maintain the unit consistency. So this two things, when R is given in kilojoules, the pressure should also be in kilopascal, or if R is in joules, you can substitute pressure in pascal. So it shouldn't get, the unit consistency should never get missed out. So once after taking care of the units, and T should be always in terms of Kelvin, where in this problem it has been already given in Kelvin. In some problems it will be given in degree centigrade or degree Celsius. At those times it should be made sure while substituting the temperature, it should be always converted to Kelvin and then substitute to this equation. Why? Because Kelvin is the SI unit of temperature. Centigrade is not the SI unit of temperature. So for any formulas or derived formulas, it is very much necessary to put it in standard SI units. So we will be finding out the value of V1, so which came out to be 0.0855. Once V1 is known, we already know the relation between V1 and V2. So V2 value comes out to be as 0.4275. So once V1 and V2 is known, we can apply every other parameter which is already known, so that I can find the displacement work. Here, since V2 is smaller than V1, also mathematically, with inside the ln function, if the numerator is smaller than the denominator, it is known to us, we always end up with negative sign. Here mathematically, yes, if the numerator is small than the denominator inside the ln function, it is very obvious, we know that it comes out to be as a negative value. Also thermodynamically, if I want to see, so already in the previous classes we have said that if the arrow is pointing towards the left side, that means the volume is getting reduced. That also means that work is being done on the system. So directly we are getting negative sign, which is a very much expected thing. If you don't get negative sign during the compression process, that means it is a questionable thing, we have done something wrong. Now it is as expected, we have got the negative sign, it is well and fine. So with this we have completed the displacement work. Next, another work need to be found, that is the stirring work. So we know the stirring work formula, it is 2 pi nt by 60 into T. This 2 pi nt by 60 is the shaft power, if the power is multiplied by time, it becomes work. Here, to avoid the confusion, just writing capital T, there can be a confusion between temperature and torque. So, I have given a small suffix Q to separate it from torque and temperature. So, 2 pi n TQ by 60 into T, substituting everything, N has been substituted in terms of Newton meter, torque, N in RPM, torque T in Newton meter, and here time has been substituted in terms of seconds. Why? Because here N is in RPM, N, that is rotations per minute, divided by 60. Now I will get it in RPS, that is rotations per second. So it is anyhow in terms of second, even though we are substituting this in RPM initially, dividing it by 60 will get it converted to RPS, that is rotations per second. So this is basically in terms of seconds. So we should also make sure that the time what we are substituting should also remain in seconds. So only one, that is the reason why 1 hour has been represented as 3600 seconds. So after solving this, we have got the stirring work to be as minus 150.79 kilojoule. So we already have the W net formula. So adding both displacement work plus stirring work. So even though we are adding it, the negative signs are getting summed up, and finally the W net what we are getting is minus 210.06 kilojoules. Moving on to the next problem. Once again we start the problem by reading it once. An engine cylinder has a piston area of 0.12 meter square and contains the gas at 1.5 megapascal. So we have an engine cylinder whose area is, the piston area is, the cross section area of the piston is 0.12 meter square. It is the cross section area. Suppose if I write the section, this is the cross section area of the piston, which is 0.12 meter square, and contains the gas at 1.5 megapascal. So it is the initial pressure. Anyhow, the area remains same throughout. So the area is always a constant value. So initial pressure is 1.5 and expands according to a process which is represented by a straight line on PV diagram as shown. Here PV diagram is part of a question, not the part of the solution. So it is embedded in the question itself. So the only given thing here is we have added rest of the other information. Initially it will be given just like this, PV diagram, just it has been given, and there is one line which has been mentioned, and there are two pressures available. This is the initial pressure P1 and this is the final pressure P2. This is the initial volume V1, this is the final volume V2. That means to say, just PV diagram, one line is given, rest of the information should be built according to the solving of the problem. So only just a simple inclined line will be shown. Then rest of the information we are going to build upon it. So then next is the gas expands accordingly to a process which is represented by a straight line on PV diagram. So as we said, the PV is given as a part of the question. We should also understand that there is no process in the ideal processes which has a straight inclined line. That is why it was a necessary for the author to give the PV diagram as a part of the question. We have never seen a inclined straight line which appears in any of the ideal processes. Basically, this process is not at all in existence and it is a customized problem. So, we need to solve it in a very different way. That is the reason why we have taken this problem. Okay. Next, the final pressure is 0.15 megapascal, that is P2. Next, calculate the work done by the gas on the piston if the stroke length is 3 meter. So, here work done by the gas on the piston, that means to say the gas itself is a system which is doing work on the piston. That is, at the end of the problem we are supposed to get a positive work. Why? Because the volume is increasing, it means to say it is an expansion process. It means to say if it is an expansion process, obviously it is a power producing process or it is a positive work. So, once I have this line, simple line, so what will I do? The area under the curve or a straight line for this case, I will try to evaluate the area geometrically. Since it is a straight line, it is very easy to find the area under this straight line in a very geometric fashion. So, what I have done? So, first I have written a dotted line below exactly below point 1 and I have written a dotted line exactly below point 2. In the same way, I have written a horizontal line starting from point 1 and a horizontal line starting from point 2. Once this process is done, we can see this entire area as one triangle and another is rectangle. So, one at a time, let us find the area of the triangle and then find the area of the rectangle, then sum it up so that it becomes the complete area under the straight line. So, to do this, so to know the area, suppose if I see the A area, so I should be knowing the base, it looks like a triangle, I should be knowing this dimension and also I should be knowing this dimension. So, let me call this as height, this as base. Now, to understand base, the base of the triangle and rectangle, let me say it as the swept volume. The piston is moving from this point to this point, that is the swept volume. The swept volume is nothing but initial volume minus final volume, or the other way of expressing swept volume is pi d square by 4 into L. You can either say it as this or as in this way. So, this I am calling it as the breadth of the triangle. So, by solving this, I got the value as 0.036 meter cube. So, the area under the curve can be splitted as we have discussed earlier into two parts. One is the triangular area and the another one is the rectangular area. So, half into base into height is the equation for the triangle area and base into height is the equation for rectangle area. So, we have substituted B value as we have already got it. If I say this is the breadth of the triangle, so that means it is the difference between the initial volume and final volume, which is nothing but the swept volume which we have already extracted it. So, we have substituted the got value which is 0.036 meter cube into height. This is the height of the triangle. So, height of the triangle is the difference in initial and final pressure. Now while taking the difference of initial and final pressure, we need to be very careful. So as it is given in megapascal, it is our responsibility to put it or place it in terms of pascal. So to do or to convert it, we have multiplied it by 10 to the power of 6. So it becomes or comes out in pascal. So all the units are in basic units. And next we have added for rectangle. So this will be the width of the rectangle, this will be the height of the rectangle. The height of the rectangle is, let me say this is 0 pressure and this is 0.15 megapascal. The difference is just 0.15 megapascal. So megapascal is converted to pascal by multiplying it by 10 to the power of 6. So summating these two values, I will be getting the value of the work. Work is nothing but the area under the curve in the PV diagram is always equivalent to the work done by the system, that is the gas, which we have got it as 29.7 kilojoules. So this is a very different problem. The reason why it is different is this kind of a straight line is nowhere mentioned in ideal gases. So it is part of the question, and also we need to solve it in a unique format, which we have not done previously in any problems. All these previous problems we were using equations, the respective ideal gas work transfer equations to solve the problems. Here we have approached and solved the problem by the geometric mean. Okay, thank you.